Hello.
Hello, sir.
I'm sorry, I wasn't. I was carried away. I wasn't mindful of the countdown timer. Like I was explaining, I said the better, the bigger the matrix size for the same FOV, the better the spatial resolution. And if you have two structures which are the same line, for one with a bigger matrix size, you're going to have a better discrimination of position than the one that has a bigger matrix size. Then for slice thickness, the smaller the slice thickness, the better for us, the better the spatial resolution. Because it's the thinner, the better discrimination we will have when we want to locate objects, want to locate structures, want to look for subtle differences. That is why today the, the trend is for us to have CT with very small thickness of a detector. Then we're looking at 1.25 millimeter, 1.25 millimeter. That is why we have 164 CT and so on and so forth. So that's it. So for us to have a better thing, let me continue sharing. So this parameter, this one will give us the best slice thickness, B, because it has A and B. So we are not choosing between A and B, because of course this 10 millimeter slice is if you look at the matrix size, we have 256 by 256 and 128 by 128. So if you want to go by that, we have D and then B. But if you want to go by the slice and thickness, we have A and D, A and B. So this is the intersection of the two. B has bigger matrix size and then smaller slice and thickness. So that's B straight away. So energy is most efficiently transferred from one system to another at what? During what? Is this a precision, the resonance depolarization, or the spin density, which is not, which shouldn't come in play? When is energy most efficiently transferred?
Resonance.
Okay.
I went for resonance too.
Okay. Why did you say resonance? Why is it not relaxation?
Well, I think relaxation, that's when they are defacing. They're defacing relaxation. And when they resonate, they have the highest, they give the highest signal. That was the reason why I went for resonance actually.
You know, for realization, you have two types of realization. You have spin realization, you have spin realization. It's not only
that's true, sir.
the spin is for phase and for the phasing of the spins. That for spin is you transfer the energy from the photons to the tissue or whatever is being imaged. It's actually resonance, but I just wanted to know if we know why we have chosen what we chose. It's actually resonance because at resonance, when you apply the frequency pulse, you have efficiently transferred energy from one system to another. But during realization, you might have, you wouldn't have the full transfer of energy because some transfer of energy will be in between the protons, whereas some transfer of energy will be from the protons to the tissue, to the surrounding tissue itself. not, I mean, I think I made a mistake in the first one. Transfer of energy will be in between the spins. The spin that's in between the protons. I think it's how they phase. Whereas the second one will be in between the protons themselves. I think the spins themselves and surround the tissue in which they are in. And it will give it will result to a complete transfer of energy. But for resonance, all the energy from the electromagnetic pulses and transfer to the body. So it's a resonance. So for 18, I think we have to go faster. Homogeneity of is as adjusted through the use of, I did say giveaway also. That was a shim coils.
Sim squares.
Yeah, shim coils. If a 1.5 MRI magnet has an inhomogeneity of 10 ppm, that's 10 parts per million, what is the inhomogeneity in hertz?
Sir, please, I need explanation on this, sir.
Okay.
Because I just say wuru to the answer. I don't know where I got this.
Okay. Okay, what is the gyromagnetic ratio of hydrogen? Let's start from there. Yeah, the gyromagnetic ratio of hydrogen. Okay, let me share the screen. I mean, let me stop the share. Hydrogen has the highest gyromagnetic ratio. Of course, that is why it is the choice and proton. I mean, the choice and it's like used for MRI. We also have other one we use. For hydrogen, per Tesla, the gyromagnetic ratio is around, I think, 43 or so per Tesla. 42.5 or thereabout. So if for the question says what is the homogeneity? If what the frequency, get the question again. If what is the homogeneity? Yes. Okay. What is the inhomogeneity? Yes. What's the inhomogeneity? Yes. What they are trying to say is um what inhomogeneity will be experienced by maybe the system or whatever. Because these are the things that contribute to some artifacts. When we're talking about T2 and T2 star, T2 and T2 sterilization, T2 star is affected by this inhomogeneity. And the strength of the effect is determined by the number of parts per million. If you have one that is a system that has 20 parts per million, it will experience maybe for 1.5 Tesla, it will experience much more homogeneity than the machine in which the homogeneity factor is 10 parts per million. So we have for this 43.1 Tesla. So we're talking about the 1.5 Tesla. So for 1 Tesla, we're going to have 40. So for 1 Tesla, we have 43 hertz. So for 1.5, I'm going to have 43 times 1.5. So So half of this is around 1 plus half. 43, half of this is around 42, 20, 21 point something. So 60, around 64. Around 64 hertz. But we're looking at 10 parts per million. Oh, this is megahertz, sorry. Megahertz per Tesla. 64. So we're looking at 64 megahertz. 64 megahertz. This is not a true homogeneity. This is the factor. So we are going to multiply this 64 megahertz by this. That is actually a factor which is 10 all over 1 million. So for 1 million, maybe hertz, for 1 million hertz, we are going to have a disruption of around an inhomogeneity of 10 hertz. So for this is 64 megahertz. This is something as 64 times 10 to the power 6 hertz. So just multiply by this. And if you multiply by this, we have, for this one, they will cancel out. This is 1 million, this is 1 million, they will cancel out. So we'll be left with 10 times 64, it's around 640 hertz. 640 hertz. So we have around 640 hertz for as the homogeneity of that system based on the homogeneity factor of 10 parts per million. Let's continue sharing. So, begin share. So we have 634. So 20, I think we should be able to finish before time. And nuclei that should be expected to use magnetic resonance signal. We have a series of nuclei. We have hydrogen, we have helium, we have nitrogen, sodium, and we have phosphorus. And which of these can be used in MRI? Which of these can be used in MRI?
D.
C.
D.
Okay. D. Of course, straight up.
I went for D too.
Yeah, you don't just go for D. It has to be D. It has to be D because, like I told you, that the numbers preceding nuclei are the atomic numbers. Of course, the atomic number tells us the number of protons. The one that have negative, odd number the protons or odd numbers and nuclei will essentially give us we can be used for MRI. So D. D is it. Which of the following statements regarding CFS compared to brain tissue is correct? Okay. Mistakenly, but anyway, I don't agree with this. I don't agree with this. I think the answer, I think it should be longer T2 and then shorter T1. But none of the answers says otherwise. None of the answers says otherwise. It can't be big. Because we encountered CFS the other time, and of course, that it had a longer T2, which is correct. But okay, you can see. I think there's a problem somewhere. Look at A and B. Okay. A and B. T1 is longer. This one is shorter. Okay, C and D. C and D are the same thing. This one is shorter, T2 is shorter, T1 is shorter, T2. Okay. I think the mistake was that come from here. It's actually, the answer is actually not here. It should be T2 should be longer while T1 is shorter. So we don't have an answer here. The answer there is wrong. This is 9. So we're going to stop by 9:30. So for this pulse sequence and diagram, we can just this one straight away. This one is our signal. A is our signal. This one is our slide selection gradient. You can see selected, selective, and this slide selective. This one is slide selective at 90 degrees. So this is our phase encoding gradient. D is our frequency encoding gradient. While at that time, this is the time the signal is sampled. At this point here, we now have our TE. This is our TE time here. This is the signal, the result, the signal. This is the readout. So F is the readout. E is the signal that was sampled. So that's about questions 20, 23, 24, 25, 26. 26 is actually this excitation pulse. A. The signal excitation. Okay. $27. Increasing the bandwidth of the slide selection pulse will give rise to what?
Increased slide thickness.
Yeah, increase the slide width. Yeah, slide thickness will increase. Number 28, which is not true. Which of these is not true? Which is not true? Are we there?
Sorry, I'm actually in a checkpoint. Driving. Both.
Okay.
We are here, sir.
Okay. So what is it? Which one is not true?
Perhaps E.
Perhaps.
I go with my chief too. Dr. Akindele. I went for E2.
You are going for him, or you think it should be it?
It should be E, sir.
Okay. Why is it not C? Because it is easier this way, because we are just looking for one option. If it had been true or false, could have been a little bit more scary.
Yes.
If the question had been true or false. So for A, true or false, B, true or false, C, true or false. This one is just multiple choice.
Sir,
Okay, I'm here.
the C Yes, looks like it too, but the only issue is that the greater always greater, and it cannot be equal. T2 cannot be equal to T1. T2 cannot be equal to T1 always.
I'm saying
C2,
C. Why is it not C?
well, C2 looks like something that can be true in a multiple choice MCQ question. So, however, um, the statement of image contrast is a blanket statement in terms of, yes, it can have an effect, but is it always going to have an, is it going to be dependent on time of inversion? Because not every time we do time of inversion for image
I think
contrast in MRI.
this should be T1, not TI. It should be T1, not TI.
Well, it's TI that is there.
Okay. T1. Okay, let's base it on T1. Why is it not, why is C not true? T1. Why is image contrast independent of T1? Why is image contrast not dependent on T1? Want to assume we see it, we have gone for C. Why would we go for C?
Well, if it's T1,
Could it be the answer if it had been T1? Or could it have
If
been
it's T1, then it will not be true, because image contrast is also dependent on T1 too.
okay, that's what I want to hear. Image contrast is dependent on T1, T2, and the proton density. The differences in this thing. Surely because of that. And even if you want to use inversion, it will depend on the TI, inversion and method, recovery method. 29. So what will be our best sequence to produce spin? What will be the best sequence for T2 among these lots?
Option B.
Option B. T2. No, it's not B. It can't be B.
E.
C.
E, sir.
C. Okay, it should actually be C. It should have a long MTR and a long TE.
That's true. That's true.
Yeah. If something was written a kind of examination condition, I purposely did that. But under exam condition, we should be able to
It's
identify.
E, sir.
Yeah,
E.
E? No, it can't be E.
No. C.
It should be C. It can't be E. The TR for E is not long enough, and to make it T10 towards T2 weighted upon sequence. Okay. Number 30, the best possible to produce a spin echo is, this one is also a giveaway question. It's a giveaway. 91A. Okay. 31. Contrast in MRI depends on differences in, okay, I think we've treated this. This one is also a giveaway. Tissue realization times. 32. The Lamont precisional frequency depends on which of these?
B.
Straight up. This is B. Let me put down much of this. 32. T2 is always what?
C.
C?
Yes, sir. C.
Okay. 1A is out. T2 practically independent of the magnetic field. Why is it independent of the magnetic field strength? For this question, T2, the answer is C, but B is also correct to an extent. B is also correct to an extent. Why? Okay. Because T2 is, well, it's okay. I think C is very correct. But I'm trying to see why B might be correct to an extent. Because T1, which is dependent on the magnetic field strength, is what will actually give us our T2 when we knock it down 90 degrees. And we remove our phase, the signal, and we turn off the RF. And then we begin to, okay. I'll go and study that question. I want to know why, actually the answer is C, and the best answer is C.
Yes, sir. But after you find the tools, we'll appreciate if you can
Okay.
get back to us on that bit too, sir.
Okay.
Thank you.
Number 34. I think 34, there shouldn't be any problem with that.
There's a gradient quest.
Yeah, gradient coils, they are used for special localization. In most biological tissue, realization times are ordered as A, B, C, D, or E.
I go for D.
D.
T2 star less than T1, then less than T2.
Why, this one should be a straightforward question. Very, very straightforward.
I think I got it wrong, but looking at it now, I will take B.
Yeah, it's actually B. T1 is always greater than T2. And T2 is always greater than T2 star. Because of the field and inhomogeneity and whatever, and then phase and the facing, and you have T2 always greater than T1. And T1 is always.
Hello, sir. Can you come?
Someone wanted to ask something. Hello?
35, number 35.
Yes.
I'm sorry, my child is distracted a little bit. Sir, can you come again on that, sir?
I said T1 is always greater than T2 straight. So the time it takes the longitudinal magnetization to go back to its original value is way.
Yes, sir. Yes, sir. It's
high.
understandable now, sir. Yes, sir.
Okay.
Thank you, sir.
Okay, we have 10 minutes to go on this. We should be able to wrap up before the 10 minutes, 9:40, 9:15 before. Okay, so we should be able to do that. Relaxation of the spin along the magnetic field is what?
Sir, is B Ti or T1?
I think it should be T1. I don't know how I made that mistake. It's T1.
It's the answer, sir.
Pardon, you said? It should be T1. B. B should actually be T1, not TI. I'm sorry for that. It should actually be T1, not TI. So which of the following will yield the highest SAR? This is also one of the safety concerns, safety issues we have in MRI. Though it is not an ionizing, it doesn't use ionizing radiation, but then there are still some very key safety issues that must be looked into. And this is one of them, the SAR. When we look at our phone, we can actually get the SAR, the specific absorption rate. This is the rate at which electromagnetic radiation transmits energy. Is that right? For some phones in developed countries, one does not sell a phone that is above some set SAR. But here, I don't think we are doing enough as to that. So this also applies to MRI. There is some procedure that will give us a high deposition of energy on the tissue. And there are some. So with that little explanation, which one will give us the highest SAR here? Is it A, B, C, D, or E? A, B, C, or D?
No idea from this end.
I said SAR has got to do with the rate of absorption of energy when we use electromagnetic waves. We use systems that emit electromagnetic radiation. And like we know, the RF pulse, which introduced into the body, uses electromagnetic wave. Hello? Yes?
Going my explanation now, I think B will be the answer, sir.
Yeah, straight off B. Because for fast spin echo, we are using a fast sequence, and again, we now introduce 6 and 180 degree. You apply 180 per TR. You've not gotten to TR, but you have applied 180 degrees refocusing pulse 6 times. So it's going to juggle the the protons in the body 6 times. They are defacing, they are growing to T1, they are defacing, and so on and so forth. So a lot of things will happen with that. At the end of the day, you're going to have, when one does this and touch the wire, the coils, you see, you can feel it hot at times. That is why people, when they are performing the MRI, it is advisable to let the those cables not twist, because if they twist, it can actually be spots where we have a local deposition of heat. So this will give us we yield the highest amount of SAR. So 38. An unshielded MR field affects the following devices except
A.
Okay.
Hello?
Yeah, hello, I can hear you. You said A. I don't think there's any problem here. It's straight up. These are electronic equipment. Some digital units, fluoroscopy units, and then some solution camera with a photo multiplied to. This should never go close to this. This one can still be manageable, of course, but this has a very serious effect on this nuclear medicine PM2. So it is an A. That's got nothing to do with this. it won't affect this. We have a little or no effect on this. So that's A. The chemical shift artifact never appears along which of these gradient directions. And which of these?
Well, I think I missed it. But looking at it carefully now, I didn't see never. It's actually face encoding. I think I choose frequency. I thought it was, I didn't see the never. It should be face encoding.
Okay.
Because it usually occurs along the frequency encoding axis.
Yes. In a way, chemical shift artifacts can actually appear along any of the.
Part of the way to correct, actually to align it in the.
Hello. We have less than 2.5 minutes. Hello. I said chemical shift can actually
Hello,
appear
sir.
along any of the direction, but in most applications, it is along the frequency encoding direction, and then at times slight direction. But when we use this method, the echo planar imaging, it can actually occur along the phase encoding when we use EPI, echo planar imaging. But for most applications in the MRI, it occurs along the frequency encoding direction. So the chemical shift doesn't appear for most, it doesn't appear along the phase encoding, except for at times during an EPF. So phase encoding or frequency encoding, of course, because chemical shift is because of the differences in the resonance frequency of fat and water to bring about because if you have fat and water in the same region being imaged in the same slice being imaged, because of the electron cloud that fat enjoys, it's going to shield it a little bit. So you have a different frequency, resonance frequency. So we might have a kind of a mismatch of anatomy, especially when we have portions that have some important part of the water. This cerebral, what's it called? When we're doing musculoskeletal imaging can be an effect. I'm less than 1 minute. Okay, number 40. The phase encoding gradient must be applied along blah blah blah. Prior to the echo, let me just do that. We have less than 1 minute. Okay.
Yeah, prior
to the echo.
Yeah, prior
to the echo.
Let me just stop this and then let me stop and then maybe 1 or 2 minutes, 1 or 5 minutes for us to do some. To end this, then you can log in again.